After checking that the Rin base is greater than 10 times of R2, we proceed to determine the voltage value of VB, the base voltage of the transistor in step 2. Using voltage divider rule over R1 and R2, we find that VB is actually equal to the voltage across resistor R2. Hence, VB is equal to R2 over the sum of R1 and R2 multiplied with the voltage supply VCC. Substituting the values of R1, R2 and VCC, we get 2.07 volts for VB. After determining VB, we then proceed to determine the value of VE, the emitter voltage of the transistor in step 3. Observe that to determine VE, VE is the difference between VB and VBE. VBE is the voltage difference between point B and point E, which is VB minus VE. Rearranging this equation in terms of VE will then give VE equal to VB minus VBE to give a value of 1.37 volts. Step 4 is to determine the emitter current IE. IE can be derived using Ohm's law by dividing the emitter voltage VE with the resistance of RE to give a value of 1.25 milliamperes. Moving on to step 5, we determine the value of the collector current IC. IC is equal to IE since the base current IB is assumed to be negligible. Hence, IC is equal to 1.25 milliamperes. Determine the value of IC, which is actually the ICQ value of the circuit. We proceed to determine the value of VCQ in the next step. To determine VCQ, we use Kirchhoff's voltage law or KVL at the output collector emitter loop. To derive the KVL equation at the output collector emitter loop, we observe that the voltage supply VCC supplies voltage to 3 parts, namely voltage across the collector resistor RC, voltage across the collector and emitter terminals VCE, and lastly to the emitter resistor RE. Hence, VCC is equal to the sum of these 3 voltages along the collector emitter loop. The voltage across the collector resistor is derived by multiplying collector current IC with the collector resistance RC. The voltage across the collector emitter terminals is VCE. And the voltage across the emitter resistor is derived by multiplying emitter current IE with the emitter resistance RE. Since the emitter current is the same as the collector current, we replace it with IC. We can then simplify the equation as such. To find VCE, we rearrange the equation in terms of it like this. To find VCE at the Q point, we substitute IC with the ICQ value which we had earlier derived and determined in the previous step. Substituting the values of VCC, ICQ, RC and RE, we obtain the value of 4.87 volts for VCQ. Thus, we can conclude that the Q point coordinates are 1.25 milliamperes for ICQ and 4.87 volts for VCQ.